Good morning. My name is Samuel, and in this presentation, I will provide a brief summary of some research related to the topic of anonymization in egocentric video. Here's an outline of what I will discuss in this video. We'll begin with motivation. We will then introduce human gait and its significance for egocentric videos in the context of anonymization. Next, we'll discuss some attacks, starting with gait recognition, and then the combination of egocentric video with third-person cameras, and finally hand gestures. Turning to the question of defense, we will discuss an anonymization strategy for egocentric videos, before concluding with a summary. Let us set out first the motivation. Why might we care about the anonymization of egocentric video? First, egocentric videos, that is to say, video taken from a first-person perspective with a camera often mounted on the head of a wearer, are growing increasingly popular. In large part, this is thanks to devices like the GoPro camera series. First-person video recording has seen a wide range of applications in law enforcement, extreme sports, geriatric care, and life logging, among others. However, it has been noted that some of the popularity of this video format may also have been driven by a second, more subtle factor, and this is that videographers may be under the impression that sharing egocentric footage does not reveal their identity. It is possible to find online egocentric videos of combat operations and even alleged recordings of robberies. Given this, it is perhaps worth asking, does egocentric video reveal the identity of the videographer? A sequence of recent works suggests that the answer is yes, at least in theory, and that in fact, wearers of egocentric video cameras may have a false sense of security about their privacy. Through a collection of techniques including recognition of gait, hand gestures, and correlating visual content against third-person cameras, it may be possible to identify the camera wearer. What can be done about this? Well, thanks to significant research and data preparation effort from various groups, a growing number of egocentric datasets have been made available for research purposes. A few examples include the GTEA dataset and its successors, editions of the Epic Kitchens dataset, and the recently released large-scale Ego4D dataset. With the availability of such datasets and efforts from other groups, there is therefore now an opportunity to study the question of how to best ensure that egocentric video meets the privacy expectations of its users. To dig a little deeper, let's turn next to human gait and its significance for egocentric video anonymity. Okay, so let us ask, what is gait, and why might it have a role to play in egocentric video anonymization? The definition of gait, as given by the Collins Online Dictionary, is someone's manner of walking, or running, or bearing. The significance of this cue relates to the idea that, intuitively, someone's gait might give us clues about their identity. This intuition has often been remarked upon in literature. Indeed, a line by Ceres in The Tempest by Shakespeare claims, "Great Juno comes, I know her by her gait." Two characteristics of gait bear on its role in identification. First, gait may enable remote identification of an individual over a large distance. It may also be difficult for an individual to purposefully disguise their gait, particularly when distracted. There are also clear limits to the use of gait as a cue for identity. It may be obscured by certain clothing, such as skirts, affected by footwear, and affected by the walking surface. It is also influenced by the physical condition of the walker, which may change over time, due to factors such as pregnancy, fatigue, injury, or intoxication. Some psychology studies on human gait have explored the perception of human motion. Johansson, in particular, considered this question in detail in 1973. Drawing inspiration from Max Wertheimer's illustration of the law of common fate using simple dot patterns, Johansen chose to study human motion by reducing it to 10 bright spots. This was achieved by collecting trajectories generated by an actor bravely wearing light bulbs, or sometimes simply reflectors, which were attached to their joints, producing characteristic dot patterns of motion for activities like walking and running. The main finding from this work was that humans can recognize walking from short clips of moving bright spots remarkably robustly, and can further identify individuals' actions like walking, cycling, and dancing. Later studies began to explore whether gait could be used as a cue for human identity. Among these works, Stevenage and her co-authors notably conducted controlled experiments to see if humans could identify individuals from their gait. Their motivations included applications such as identifying a bank robber whose face was hidden during the robbery amongst a lineup of suspects. Their experiments found that human subjects could indeed learn to recognize individuals among 6 walkers matched for build and height who were dressed in black and wore balaclavas while they walked in various lighting conditions. This identification was successful even when point lights were used in the style of Johansen. Further experiments, based on the idea of an identity parade of criminal suspects, illustrated that participants could identify individuals far above chance accuracy. The broader conclusion of this work is that humans can sometimes recognize individuals from their gait without body shape information, if they are given a small number of examples to learn from. Among the first efforts to employ computer vision to automatically infer identity from gait, Nixon et al. Explored 2 approaches based on low-level cues. The first, which they termed statistical measurement, performs PCA on sequences of walking pixel images, producing eigenvectors, also pleasingly termed eigengaits, that capture the directions of maximum variance in each sequence. A canonical space transformation is then used to map trajectories into a more discriminative space in which identities can be compared. A second approach, termed feature-based measurement, first performs edge detection on walking sequences to estimate limb positions using a velocity Hopf transform to improve noise robustness. A spectral signature is then generated with a Fourier transform from the periodic motion of leg movements for each sequence, enabling k-nearest neighbor classification on test sequences. Both approaches achieve promising results on a small dataset across 10 subjects. Follow-up work from Wang et al. Showed that silhouettes can be used to identify individuals from their gait. Their algorithm first performed frame-level segmentation on walking sequences to localize the human, then performed silhouette tracking across frames. Similarly to the work of Nixon, PCA was used to reduce the dimensionality of the sequences, in this case on top of boundary features, before a classifier based on nearest neighbors discriminates identity. In addition to a method, this work also introduced the NLPR dataset of 20 individuals and 240 walking sequences to enable a more systematic comparison of early techniques. Finally, a third method moves away from vision and instead employs accelerometers. The motivation for such an approach is that mobile phones are ubiquitous and they contain a lot of personal information, so Gait may provide a useful authentication signal to secure these devices. The method employed here was to use simple template matching across normalized time signals, which experiments showed to work well across a collection of 36 individuals at different walking speeds. Now that we're a little more familiar with Gait and previous work that has used it to identify individuals from their walk, we can return to the topic of egocentric video and how gait recognition may be used in an attack. The work entitled An Egocentric Look at Video Photographer Identity by Hoshin and Peleg in 2016 focused specifically on the problem of identifying a videographer in egocentric video. The key idea behind this work is that egocentric video can effectively serve as a kind of head-mounted visual gyroscope that captures body motion. As a result of this, egocentric video can reveal videographer identity in a similar way that gait recognition reveals identity. To explore this hypothesis, the authors construct experiments for videographer recognition and verification. First on the first-person social interactions dataset, and second on a newly collected EVPR dataset spanning 36 individuals recorded with GoPro cameras. The features used to tackle this problem are a collection of sparse optical flow vectors across 4-second sequences of frames. These flow vectors are shown to qualitatively capture identity. Here, the temporal spectrum associated with the same individual, user A, shown by the red and black lines, exhibits greater similarity, despite the fact that they are recorded on different cameras, than the similarity between the blue dashed line and the red line, which use the same camera for different individuals. This suggests that these vectors may be capturing something about identity. To encode this information for identification and verification, a CNN is used. This approach yields 91% accuracy on a 20-way recognition task on a test set recorded by camera wearers taking walks 7 days after recording their training sample videos. The data was collected in this way to minimize the chance that the model could cheat by recognizing similar conditions rather than gait. These results are promising. The authors note some failure cases for this approach, including motion blur, resulting from sharp head turns, and the presence of large moving objects like cars, which can cause unusual flow patterns. Next, we will consider potential attacks arising from the combination of egocentric video footage with third-person video footage. One early work that showed the possibility of identifying egocentric camera wearers with external footage was the Ego to Top work by Ardashir and Borgi in 2016. The key idea behind this work is that surveillance cameras and drone footage are often captured from a top-down view, and that these videos can be correlated with egocentric recordings made by multiple individuals to solve a who is who problem. The formulation considers a setting in which we have a collection of egocentric videos from different camera wearers in a scene, together with a top-down video of the same scene, and our goal is to determine not only whether the scenes correspond, but also to link the egocentric video to specific individuals. For example, here, I think this person, highlighted in green, corresponds to this egocentric video. The authors conduct experiments that show promising results on 50 test sequences, both indoors and outdoors, with different numbers of humans. They find, perhaps unsurprisingly, that performance improves as the number of egocentric camera records increase. The assignment method used in this research works as follows. We begin with a collection of egocentric videos and a top-down video. For the egocentric videos, we build a graph that captures the relationships between the recordings, treating each recording as a node, while in the top-down view, we construct a similar graph, except that it is now done between the visible people. We then apply graph matching to find a soft assignment that represents the best correspondence between nodes in the two graphs. And finally, convert these soft assignments into hard assignments with the Hungarian algorithm. To build the top-down graph, multi-object tracking is first used to compute trajectories of visible people. Then, representations are constructed for each node based on the overlaps between the field of view in each frame and the number of visible people. The field of view of particular people is illustrated here with bright green lines. The idea is that frames with a similar top-down field of view will be likely to have similar visual appearance in the egocentric videos, allowing us to match them. To build the egocentric graph, the number of people visible in each frame is estimated with an object detector. The intuition here is that if we compare the number of people visible in the top-down field of view with the number of people visible in the egocentric views across frames, we should see a clear correspondence if we have a correct assignment. Second, gist features are computed to estimate visual similarity between frames. Then, given gist similarities in egocentric videos and field of view overlaps in the top-down view, we can use 2D cross-correlation to find the best alignment between them. Using these pairs of similarities, together with some others, we can employ spectral graph matching to match graphs and post-process the result with Hungarian matching to produce our final assignment. The work identifying first-person camera wearers in third-person videos by Fan et al. Pursued the goal of finding correspondences between first-person camera wearers and third-person static views, but without the constraint that the third-person view is top-down, as we saw in the previous work. So, given a third-person video and a first-person video recorded within the same scene, the task is to identify which person in the third-person video corresponds to the first-person video. The key idea behind this work is that corresponding video from each view will likely share some visual evidence in the form of similar appearance or motion. We can therefore learn an embedding to reflect similarities across views. Note that by using third-person footage, it now becomes possible to recover the appearance and indeed the face of the egocentric videographer. To implement this idea, the authors proposed to train a dual encoder with a triplet loss. This encoder operates on appearance cues from RGB frames, in which individual persons are excluded with bounding boxes in the third-person view, and on motion cues from optical flow. Together, these produce a two-stream embedding with vectors that are close if and only if the two views are in correspondence. Experiments are conducted across 6 indoor environments with multiple camera wearers, where the authors show that the embedding approach improves significantly over simple baselines like directly using frozen CNN features to establish correspondences. 2 particular kinds of failure case are noted. The first occurs due to similar egocentric motion across videos, such as when one person is sitting down and another is nodding. The second stems from person occlusions, leading to a failure in the appearance stream. The paper Is Sharing of Egocentric Video Giving Away Your Biometric Signature by Thapar et al. In 2020 considered the problem of whether the identity of an egocentric videographer could be matched against third-person footage with no overlap in content. The key idea used in this work is that Gait can be estimated both from sequences of egocentric footage and from third-person footage. To highlight this point, the authors illustrate the optical flow computed from egocentric footage of 2 human subjects as they take different steps in the Gait cycle, noting the distinctive differences in flow between the individuals. The method proposed in this work takes as input first-person video and third-person video, and aims to perform cross-domain matching to determine whether they correspond to the same person. The first-person footage is used to compute optical flow and mapped via LSTMs into a sequence of embeddings, while the third-person footage is processed by an off-the-shelf Gait feature extractor. These embedding sequences are projected via networks trained with a triplet loss, then combined to form the basis of a distance indicating whether or not the 2 inputs lie in correspondence. Experiments are conducted on the FPSI and EVPR datasets mentioned previously, as well as on a newly collected dataset of 12 subjects spanning both egocentric and third-person views. Evaluations conducted under both closed-set and open-set protocols demonstrate some degree of successful identification on the new dataset. We turn next to hand gestures. A second work by Thapar et al., entitled Recognizing Camera Error from Hand Gestures in Egocentric Videos in 2020, considered a different question. Can an egocentric videographer be identified from footage of their hands? Given sequences of frames like these, the aim is to identify which hands belong to the same person. In this particular case, if you are wondering, the first and third rows belong to the same identity, as do the second and fourth rows. The authors consider closed-set identification and open-set verification formulations of this problem on the Epic Kitchens dataset, which at this time contained 32 subjects. Their goal was to determine whether they could recognize videographers within the same activity, across activities, or even in an open-set verification setting, in which the aim was to match videographers that were unseen during training. The proposed approach takes in an egocentric video segment and extracts from it optical flow and hand masks. Each of these is mapped through an architecture called Ego Hand Net. The hand mask stream is then used to gate the flow features to produce a final embedding. The Ego Hand Net architecture itself consists of applying spatiotemporal feature extractors across frames and aggregating the results with a sequence model. The model is trained either directly for classification or using a triplet loss for verification. The results obtained with this model are significantly above chance for all three problem settings considered in this work, spanning both identity classification and verification. Qualitatively, a t-SNE plot provided by the authors suggests that the learned embeddings coarsely group by identity. Each of 28 identities here are indicated by different colors. Having discussed some ways in which egocentric video leaks identity information, we now turn to a defensive anonymization strategy. Following on from their previous efforts, Thapar et al. Turned to the problem of anonymizing egocentric videos in a 2021 CVPR work. In particular, the problem they pose is, can we anonymize egocentric videos against identity attacks? The key idea pursued in this work is to apply perturbations to the video footage that will fool identification attacks based on recognizing gait or hand gestures. In particular, the goal is to find perturbations that are effective at protecting identity, are visually imperceptible so that they don't harm the quality of the video, and preserve task performance for other useful systems, such as activity recognition or object recognition. Given frames of an egocentric video, one approach could be to simply add random noise to the camera motion. However, this produces fairly aggressive distortions, many of which don't contribute significantly to identity protection. The perturbations proposed by this work are subtle and difficult to notice, but are effective at resisting identity attacks. The method employed here assumes that for a given target video that we wish to anonymize, we can also randomly sample a gallery input video whose videographer identity differs from the target. Operating on blocks of 16 frames at a time, this gallery video is pre-processed with a SLAM pipeline to estimate a sequence of rotation matrices, represented via Euler angles. This is a sequence that we expect will contain information about the identity of the wearer. Offline, we assume that we have trained an architecture called Ego IDNet on top of this sequence of rotations, which employs projections with self-attention and average pooling to produce a feature vector for classifying the identity. Since the network has been trained for identity recognition, we can apply guided backpropagation on the gallery input video to identify the components of the input rotation sequence that were salient to the identity classification. These rotations are then combined with camera intrinsics to compute a homography that is applied frame-wise to produce the final anonymized video. The essential idea is that the final video will contain 3D camera transformations that represent a blend of two identities, the identity of the original video and the identity of the gallery video, making it hard to distinguish them. In experiments, the authors demonstrate first that EgoIDNet outperforms previous identity attacks that employed optical flow and is particularly effective in open set evaluation conditions. To explain this finding, they suggest that 3D camera rotations are less prone to overfitting than optical flow-based attacks, and thus generalize better. Next, experiments are conducted using randomly sampled rotations. These degrade the performance of an identity tag, shown here in teal, but also significantly harm activity recognition performance, shown here by orange, red, and grey bars, where the x-axis corresponds to the magnitude of the perturbation, increasing from left to right. By contrast, the perturbations obtained via guided backprop reduce the effectiveness of the identity attack, again shown in teal, but only marginally affect activity recognition performance, again shown in orange, red, and grey. Further experiments are conducted on the FPSI, Epic Kitchens, and IIT-MD WFP datasets to show that these findings generalize to some extent. Okay, let's wrap things up with a summary. Egocentric footage is on the rise, benefiting from improved hardware such as the GoPro camera series, among others, and its range of useful applications. However, some caution is required when sharing footage, since several identity attacks have been demonstrated on the videographer even when they are not visible in the footage. These attack cues include the videographer's gait, hand gestures, and linkage attacks against third-person footage. One potential anonymization strategy has been described based on selective perturbations to the footage. It's worth noting a few limitations and caveats. First, these attacks have been studied with relatively small numbers of subjects, which limits the statistical strength of the results to some degree. Relatedly, many methods use deep neural networks that are difficult to interpret, and there is a chance that the models are exploiting biases in the data in ways that are non-intuitive and do not generalize. It's worth noting here that Thapar et al. In their 2020 work did make an effort to interpret their flow features, though this is in itself a challenging task. Despite these caveats, these works nevertheless represent valuable proof of concepts, with larger scale confirmatory studies as a natural next step, indicating that the topic deserves further study. Finally, a caveat relating to this video, rather than the research itself, I'd like to note that this review represents very much an incomplete summary, with the goal of providing a brief introduction to the topic, rather than a comprehensive overview of the research literature. That's it. We've reached the end. Thank you very much for your attention.